Thank you very much. Thank you very much for inviting me here. It's a real pleasure. And today I want to describe how somehow some tools that originated by algebraic topology can be used also in the realm of p-adic Hodge theory to define and study and have alternative approaches to rigid cohomologies, or more generally to p-adic, or not necessarily p-adic cohomology. So I will start with a brief introduction of these tools and the questions that I will try to solve. And then on the second part of my talk, I would maybe give some hints to a work in progress with Arthur César Lebras about a new cohomology theory in this direction. So let me start with this introduction. So somehow often in p-adic Hodge theory, but not only there, when defining cohomology theories, we do the following. We make choices. We make non-canonical local choices. And so you have an object, and maybe locally you can perform some choice, and then you use this choice to define some cohomology theory, and then one proves that they glue, these definitions glue via some descent, and maybe that they do not depend on these choices. Typically using some homotopy. So before going on, let me make some examples where this happens. Let's say for rigid cohomology, as in the work of Moschew and Waschnitzer. So the idea is to associate to a algebraic variety over a perfect field in characteristic P a formal scheme over the Witt vectors of the rest of the field, or more generally to some DVR or something like that. And then once you have a formal scheme, you can literally take its generic fiber over the valued field, which will be a rigid analytic variety. But the first association that we have here, it's not at all canonical, it's not at all functorial, it's not at all possible, even in general. There are many counterexamples to this, but at least locally, if X bar is smooth, you can choose such a lift, a smooth lift. Okay, so this idea somehow that can be seen in the work of these authors is that as soon as you want to define a cohomology theory over here, over a field of characteristic P, then somehow you can change characteristic and go over something which is mixed characteristic, but it's a rigid analytic variety. A second example of this is the work of Grosse-Klöne. Well, up to now, nothing, but then if you glue together with the second part, which will be how to define de Rham cohomology theory there, then by precomposing with this functor, you would get rigid cohomology a la Moschew-Waschnitzer, and that does not depend on any choice that you make here. So what is the problem here? Is that even for rigid analytic varieties, even if we are over a field of characteristic 0, the Rham cohomology is ill how to say, it doesn't behave well. So how to do this? If X over K, which is a non-Archimedean field of characteristic 0, how to define a well-behaved de Rham cohomology for it. So what you do, we can locally say it's smooth. You can locally choose some strict embedding of X inside a strictly bigger rigid analytic variety X prime. This structure is typically denoted with a dagger because it's called a dagger structure on X. And once you make this choice, you can then look at the complex of X dagger over K, which is a subcomplex of the usual de Rham complex, made of those forms that extend to some strict neighborhood of X inside X prime. And then you can use this complex to define a cohomology theory. And you have to, if you look at all the papers from Geobe-klionne, you would notice that you have to prove that this does not depend on the choices that you make. And this is what we typically call the overconvergent de Rham cohomology for X. And there is a more recent example of this situation. It's a link to Bhatt-Monow-Khoze A-inf cohomology, or more specifically to its relation with the crystalline cohomology. What you have is that if X, curly X, is a smooth formal scheme over OCP, say, so you can locally, you can choose some nice coordinates landing to the formal ball, SPF of OK, T1, Tn. And then you can use these nice coordinates to perfectoidify curly X, which is an operation that you're not allowed to do in general when you are in characteristic 0. There is no canonical perfectoid cover of a rigid analytic variety. But then if you have a choice of coordinates, you can take the base change to the somehow more canonical perfectoid ball here, and you can take this thing and use it to define, then this is a perfectoid space now, so it makes sense to consider its value of B of X hat, and then you can descend back to something which is depends on X by performing some Galois cohomology and taking some décalage functor, and then you would get a nice cohomology theory. I've chosen here B, which is somehow not the choice of Bhatt-Monow-Khoze, which is more precise. They take A, so the global sections of the formal, of the relative Farfontaine curve, but in somehow the integral version of it. This is a rational version of it, but you can do the same thing. And so, as you see, it's not clear that this nice cohomology theory does not depend on the choices that I've made along the way. But, well, if you look at this article, and as Kiran said, this is related to the fact that it's just some pro-etal cohomology group of the original rigid analytic variety. And, but the fact that you need somehow to choose coordinates at a certain point is when you want to prove that this Bhatt-Monow-Khoze cohomology relates well to crystalline cohomology. So in the proof of this compatibility of this isomorphism, they do choose coordinates and then prove that this choice of coordinates doesn't really play a role and stuff. Okay. So as you can see, there are several instances where you do local choices and then you try to glue them up. And so the main question I will try to explore is what is the best let's say, the most precise way to rephrase these constructions. And can we get something more out of it? So at each instance, you see we've done some local choices, and typically in order to prove that they are not, the choices are not really relevant, we introduce homotopy. So it's pretty natural, I would say, to introduce motives for complete this task. So let me recall the definition of motives. So the aim is to construct an environment where you have descent and homotopy invariance. So what you do, you simply consider the universal category where this happens. So what does that mean? You start with your arbitrary site, and then you choose an object inside the geometric category C, and then out of this datum, so C in particular embeds via Dionida in pre-sheaves of C with values, say, in complexes of lambda modules. So I will write this as complexes of pre-sheaves with values in lambda modules, lambda being a ring containing Z1 over P. So P is inverted, and P is any prime that plays a role in the theory. So if C is the category, say, of rigid analytic varieties, I would like to invert the residue characteristic. Okay? If it's smooth schemes over K being of characteristic P, I invert P, just for the sake of simplicity. This is complexes of pre-sheaves from C with values in lambda modules. Or if you prefer, pre-sheaves from C with values in complexes in lambda modules. If you prefer, this already enjoys a universal property, because you know that pre-sheaves enjoy a universal property, they are co-complete, but then if you want to do homotopy, you'd rather want to derive things, so introduce complexes. And then what you do, you can insert artificially descent, and once you do that, you simply pass to sheaves. And then finally, you want to impose homotopy invariance. So you mod out this DG category. So every time I write here complexes, I rather think of the derived category maybe. And then I impose descent by imposing that all the maps of the form x times I going to x must be invertible. So you reinforce, you impose this as a condition. So as you can see, more or less, I've constructed a category out of which has the free universal property, and then I imposed descent and homotopy. So I'm just doing the universal category where this happens. In modern terms, this is the infinity category, lambda enriched infinity category of sheaves, of I invariant sheaves. Okay. So examples of this. One can take C to be smooth varieties over a fixed scheme, X, and tau to be the étale topology. Whenever you are in the algebraic world, you typically take your interval object that you are somehow contracting to be A1. And this gives rise to the category of motives that we typically denote by dA x lambda. But of course, you can be more, you can have more creativity and then rather take rigid analytic smooth varieties over a fixed one with the étale topology, or maybe the overconvergent guys over a fixed base, or even perfectoid smooth spaces over K being a perfectoid field. Where with perfectoid smooth, I mean some adic space, which is locally étal over the perfectoid ball over K. And anytime you make these choices, then this would give rise to the categories that I would typically denote by ridge dA or perf dA or ridge dagger dA or something. Okay?
So you're thinking of perfectoid, are these perfectoid things, or can you have a smooth thing over a perfectoid?
These are perfected spaces.
Perfectoid things which locally.
Yeah. Of course, if you can be even more creative and then put here any adic space, and then you would impose that they are locally étal over the relative perfectoid ball, then it would be no longer perfectoid spaces in general. So more generally, there is an extra step that one does, is that one inverts also the Tate twist. So there is a way to define this object in this category. This would be a direct summand of the circle. And as you know, normally cohomology theories have the Tate twist inverted, so you impose that the Tate twists become invertible. This is, again, something that can be performed in the realm of DG categories, and this is what people would typically denote by DA, or sorry, motives, like stable motives. So by dropping then the appendix F, okay? DA is the DAF, where I invert the Tate twist formally. What it stands for? Derived abelian? I have no clue. I'm sorry. What is some remarks? So if you are more familiar with Grothendieck motives, they would have Chow groups inside and cycles and correspondences. What is the relation with this definition that I just gave? So if you use correspondences rather than simply maps of rigid smooth things, then you would get, and you would follow the same steps, then you would get what people typically denote by dm or dmf of, say, x lambda. And but there are some nice theorems that say that dA of x lambda is the same as dm of x lambda, even ridge dA of x lambda is the same as ridge dm of x lambda. So in order to, this is a technical point if you want, but this tells me that automatically in these categories I have correspondences. For some magic, because of these sheafy things, I automatically have, so I can use alterations to make some computations in this category because they just simply behave like their counterpart, the M, but they're easier to define. Yes, indeed. And just to make a quick recollection of who proved what, so this is a standard statement. This can be seen already in Morel's work or Szynski-de-Gliese. And then also Ayub has an effective statement, and this was a generalization of mine, and to be completed with a recent work that I did with Bambots. So this is old, but this is 1990. So another nice feature of these things is that they are quite explicit. In the sense that you can really make computations. It's not like a mysterious formal thing that lives up in the clouds. You can really use some geometry and get some statements, concrete statements that typically boil down to some real geometry there. On the other hand, by their definition, they have a universal property. which tells me in particular that, say, you have a nice cohomology theory from defined over smooth varieties over a field, landing in, say, lambda modules, or d lambda. Well, if it is a nice cohomology, namely if it has descent with respect to the étale topology, if it is homotopy invariant, if the Tate twist gets inverted, then automatically it factors over the category of motives. Defining, therefore, a functor between DG categories, which is typically called the realization attached to H. Okay? This exists, unique up to some homotopy. So what does that mean? Is that the main point I'm trying to make is that sometimes it is even easier to define this realization functor than the actual cohomology theory. And another thing is that you can use the properties of motives to get something on the cohomology theory. Okay? This is the whole point of my talk, and I hope that I will convince you of these things at the end. Let me start by an easy example of this phenomenon. So you take, say, smooth varieties over C. Then you can analytify them, right? And they become smooth manifolds over C. So since the motivic construction has a universal property, in particular it would be functorial, so this would create a functor from motives over C to analytic motives over C. Okay? You can also include the point inside this category, and so this would create a functor in the opposite direction on the, let's say, the category of complexes on lambda. It turns out that this functor is actually an equivalence. In other words, the motivic homotopy theory for complex manifolds is trivial in the sense that the datum of a complex manifold is just the datum of a complex of lambda modules. Okay? This is not that hard to imagine since we have imposed descent and we have contracted the disk. So in analytic manifold is always locally a disk. So if you contract them, then you have just reduced any manifold to a bunch of points and arrows between them, namely a simplicial datum. Okay? And so what you get automatically out of this observation, you can associate a motive over C, a complex. Well, it turns out that this relates to the fact that X goes to its Betti homology, right? Because I'm analytifying them and then taking this simplicial thing. This is just the Betti realization, and as you can see, this is a more direct way to define it. Well, it's not really more direct because Betti is not that hard to define. But maybe more interesting for you is what happens with the p-adic Hodge theory. So now suppose that K is a complete non-Archimedean field, no, not really, a complete valued field of mixed characteristics. Then you can define the category of formal motives over its ring of valuation. And then if you have a formal scheme, you can either associate the special fiber or the generic fiber, right? And this is continuous functors, so it defines automatically some functors between formal motives landing to motives over the residue field on the one hand, or rigid motives on K on the other hand. All right? Here somewhere we also have the category of dagger motives where we started with the category of rigid analytic varieties equipped with this extra choice of this local embedding and stuff. But what we can do, we can simply forget this extra structure, taking this embedding to its limit. And this also defines a continuous functor, so in particular a functor at the level of motives. Okay? At this level, so here you remember this was a quotient of a category of complexes of pre-sheaves. So in particular, a natural object to study here is the overconvergent de Rham complex, the pre-sheaf that associates to each X dagger the complex, the de Rham, overconvergent de Rham complex of X dagger. This is a complex of pre-sheaves, so it naturally lives here as an object. And it represents the overconvergent de Rham cohomology. So this is overconvergent de Rham. Okay? But now, this diagram, this is an equivalence. And this is also an equivalence. Moreover, if I have here algebraic motives over K, I can take here the analytification functor, and this is not an equivalence, yet it's somehow essentially surjective in the sense that this category is generated by the analytifications of algebraic things. So this is a statement that we'll call heart, these I will call clubs, and these I will call spades. And again, who proved what? So heart is a theorem of Ayub. It's not that strange, because you know that it's somehow related to what I told at the beginning. Locally, you can always lift something smooth to a formal smooth, and you may do so up to homotopy. So it's sort of, it doesn't shock you, I hope. And also this is not that shocking, because there is this Artin's approximation lemma saying that you may choose an overconvergent structure, but they will be equivalent up to homotopy. So once again, this gives you a feeling of why this should hold. And the proof is not simply that, by the way, but this plays a role, and this is a statement of mine. Once again, you have to update everything with this more recent work with Bambozzi about more general rings of coefficients. And also, spades is a result of Ayub. And this result is slightly more shocking, because it tells you that rigid analytic cohomologies somehow can be tested on algebraic things. So their properties can be tested on a specific set of generators, and you can choose, say, proper smooth algebraic varieties to test so. So this may sound shocking, but if you look in the proofs of Berthelot and Geobe-klionne about the finiteness of the de Rham cohomology, of the overconvergent de Rham cohomology, they boil down eventually to such approximation and alterations, reductions to algebraic statements for proper smooth algebraic varieties. But what we get out of this diagram? You see, I have defined a cohomology theory by composition for rigid analytic varieties, and I have defined a cohomology theory for algebraic varieties over the residue field. And this is a completely alternative way of defining it with respect to Berthelot's strategies. Not only can you prove that they exist, but as a corollary, you also get that rigid cohomology and the Rham cohomology for the rigid analytic varieties are well defined, but also they are finite dimensional on quasi-compact things. They have étale descent. You can prove Kunnet, like a bunch of formal things. This is, once again, it's not a completely original statement, because this was somehow well known, at least in case K is a discrete valuation. So OK is a DVR, or maybe CP. But this is more slightly more general. But the proof, I think, is more immediate. OK, there is a third instance I want to talk about. It's the recent work by Arthur César Lebrun. He proves that if you have overconvergent smooth variety over CP, you can associate to it a version of Bhatt-Monow-Khoze cohomology, but a rational version of it, so using B rather than A. And this is the usual definition, but now I can make it overconverge by taking the limit over H's, because every time you have an overconvergent structure, this can construct automatically a tower of strict neighborhoods of your limit. And so you can perform functorially this, and now using motives, he proves that this gives a functor from motives over CP landing in modules over the Farfontaine curve, and once again sending something compact to a vector bond, to something whose cohomology is a vector bond. So this is very interesting because this is a way of getting vector bundles on the curve. Say it again? Yes. I'm sorry. Lebras. This is whole point 3 is his strategy. Okay? There is another thing you can do, is that now suppose that K is perfectoid. I'm sorry, I know everybody hates when one does that, but then you have also perfectoid motives over K. And maybe they are the same as perfectoid motives over the tilt field, and here you have motives over the tilted field, K flat. This is given by the canonical perfection morphism from motives over here to motives which are perfectoid. This is the Scholze's tilting equivalence, which in particularly gives an equivalence of motives for smooth things. And here there is not really a direct geometric functor, but there is maybe the diamond construction somehow. You can associate to a rigid variety the sheaf it defines on a category of perfectoid spaces. Well, again, this is an equivalence. And this also is an equivalence. And this is an old result of mine to be updated with some recent thing with Bambozzi. And since I have expanded my diagram in equicharacteristic p direction, what do I get? I get a de Rham-like cohomology theory for smooth perfectoid spaces and for rigid analytic varieties in equicharacteristic P. And this somehow is already a new feature because, to my knowledge at least, there is no classic cohomology theory associated to rigid varieties over an equicharacteristic P thing. So what does that mean? If you have a family, xt over fpt, which is generically smooth, so at 0 it can behave very badly, you are somehow able to associate to it log rigid cohomology of the special fiber at 0, let it be awful as it wants, and of course this definition is compatible with usual rigid analytic rigid cohomology or log rigid cohomology whenever the reduction is semi-stable. Okay? So this is a new cohomology theory. The bad thing is that where does it land? In order for this diagram to make sense, at this instance, I have to choose an untilt of k tilde. So if I start with such a family, at a certain point I have to choose, so we're taking values in d k sharp for some k sharp, which is an untilt of fp double bracket t it's perfection, completed perfection. And as you know, there are many of them. So let me compare for a second the last two methods that I have sketched. So under Bhatt-Monow-Khoze-Libras method, so we get a vector bundles on the curve, which is very nice, an object. But the bad thing is that we start from the point at infinity of the curve. So somehow we have chosen the point at infinity because everything was defined over Cp, and out of it we defined a vector bundle on the curve. So since we want to define something global on the curve, maybe we would like to start directly in equicharacteristic P. This would be more natural. And then another, then this last approach. So maybe the RAM things taking values in K sharp. It has the advantage that we start at case flat, so there is no choice of the tilt as the starting point. But the bad thing is that we have a pointwise theory. So at every choice, at any choice of your rigid point on the curve, you would get a vector space out over this point. But it's not clear that they glue together into a vector bundle. So I write pointwise vector bundle on the curve in the sense that these are just collections of vector spaces on each ridge point. And so the aim of my second part of the talk is try to unify the good things of these two approaches together. So we want to something that enjoys both pluses. Okay? Another thing that regarding this definition is that the décalage functor is used. Somehow the décalage functor is not that geometric or is not that intuitive, at least to me. So maybe we will try to get rid of it. But in order to do so, I am sorry, I have to talk again about some motivic properties of the stack they form, stack of motives. So because of this universal property they enjoy, every time you have an arrow x to y, say in between smooth rigid spaces or adic spaces or whatever, they don't have to be smooth. Then this automatically induces a functor from the motives over y to motives over x. Okay? This is defined by taking the pullback along f of smooth things over y. They would define something smooth over x. This is continuous, blah, blah, blah. And so as you see, this is like a pre-sheaf of DG categories on rigid analytic spaces. And of course, since we are imposing a tal descent pointwise, we wonder whether this pre-stack or whatever enjoys some descent properties. And this is true. So by some infinity categorical nonsense, I mean, this is not formal. These are statements which are needs to be proven. It's not something obvious. This forms an analytic stack of infinity categories, or you prefer DG categories. What I mean by that is that, say, X is the union of U and V, and then motives over X will be the homotopy limit of motives over U times motives over V, going into motives over the intersection, stuff like this. We can also be more precise. This association actually enjoys some étale descent, even more, some étale hyperdescent, but I won't need that. So since we have something that enjoys descent, whenever we are interested in its properties, we can look at what happens at stocks, because this is what is most important. And this is another, okay, so sorry, who proved what? This, I said, this is categorical nonsense in the sense that this can be considered folklore but by many topologists, but this is a statement that you may find in Lurie's book. But I'm sure he was not the first to know this. So what happens at stocks? So if X is a point of a rigid analytic space, then what is the stock? So I take the limit of motives along opens U that contain the point. Well, it turns out that this is isomorphic to the category of motives of the residue field. So of the adic space that is attached to the point X. As you know, every point of an adic space, or say it's analytic, I don't want to, any analytic point gives rise to a valuation, so therefore attached to a valued field with a valuation ring. It may not have height 1, so I need to keep this pair here. And it turns out that the stock are really just motives over points. So this is a very nice proposition, and this is it's not that hard, but the proof, I'm not sketching the real proof, but once again, I'm trying to convince you that this makes sense. And this is just this remark. Every time you have an analytic point, you know that if you take the stock of the sheaf OX and the pair OX plus, and if you perform their completion with respect to some local pseudo-uniformizer, what you get is automatic KX plus. So somehow the fact that stocks are fields is something which is a standard for adic spaces, analytic adic spaces, and it is a crucial property that has been already exploited by Scholze in his first article on perfectoid spaces. So it is not completely weird to re-see this property for motives, once again. Why? Because this tells you that somehow this is the inverse limit of the neighborhoods of X, so you can lift finite étale things from the point to a neighborhood and stuff like this. Now, another property that I will use is that if K flat is perfectoid of characteristic P, then you have in here, you have an action phi. It's a natural transformation from the Frobenius to the identity, which is given by the relative Frobenius. We are in characteristic P, so this exists and it's well defined. Well, it turns out it is invertible. So in other words, the local Frobenii are invertible in motives. And here is an instance where I use this magic trick where I put correspondences formally, and as correspondences, the Frobenius is much easier to to be shown to be an isomorphism because it has a transpose, and so if you compose with its transpose, you just get a power of p being invertible in the ring of coefficients, it's an isomorphism. So let me put this formalism together to get something geometrically interesting, I hope. So this is a work in progress with Arthur. And so what we start? So we start by K flat, which is a perfectoid field in characteristic P. Yes? I'm about to define it, I'm sorry. So you can see, Kiran already talked, or I think everybody knows now after 1 week of lectures that you can define SPA of W of O, K flat, and take its analytic points. In other words, you just remove the non-analytic point, which is given by just little k. And I like to depict this as a sphere rather than as a quadrant or whatever. So here somewhere there was this closed point that was little k. I dropped it out, so I'm left with this. Somehow here I have the point k flat, and here I have the point w of k 1 over p. Normally there is a parameterization of this sphere, this being 0 and this being infinity, and I also have an automorphism phi that pushes things away from k flat. I'd rather use phi to the minus 1 pushing everything to k flat. Okay? Now I use this adic space, and I use this fact, right? So if I apply it to the point k flat, maybe I should call it x flat, I don't know, I get that motives over k flat are the same as the limit of motives on a family of opens containing this point, right? And if I fixed U to be one of them, a compact one, then I can simply take its image by phi to the minus 1. So I have that this is the limit of the motives of phi to the minus n of U, as n varies. Once I fixed U to be some quasi-compact neighborhood of x flat. Okay? So this tells me that anytime you have a motive over this point, you can extend it a little bit on a neighborhood of it over the Farfontaine curve, right? So if I have M flat, this would define some MU defined over some neighborhood U of the point. And more than that, I just proved that the Frobenius is invertible at this level. So this gives me some gluing datum of this. So I would have that MU restricted to phi minus 1U, phi upper star is the same as MU. So I have something defined over U. I have some gluing datum with respect to the action of Frobenius. So by gluing this together, I can land into motives over the whole curve 0, infinity. Right? Because I have something on U, it glues well, it behaves well with Frobenius, so I can glue them together, patching them along this Frobenius. And of course, I will be able to cover the whole curve, but the last point, which is not taken from this action of Frobenius. But this is not really important, because the Farfontaine curve is fully covered, so I can restrict to the Farfontaine curve somehow. So first by restricting over the space 0, infinity, and by its explicit description, this factors over motives over the curve. So this way, I have expanded something that was in the point at 0 slightly, and then the Frobenius allowed me to cover the whole Farfontaine curve by then quotienting by phi. So this is already a nice thing to have, but it's not really. So what to do in order to produce a vector bundle on the curve? I have finally something which is relatively smooth over the curve. I can pretend it's also over-convergent. So I can just go to O XFF modules by taking the over-convergent de Rham realization. And then, so what I have constructed is a way to produce out of a motive over K flat, a motive over the curve. And what happens if I restrict to some untilt, a fixed untilt? Does it behave well? That this is the isomorph, the equivalence that I had shown some time ago. And how does it compare with the relative curve that the construction that Kiran sketched before? If you start with something perfectoid, then there is a way to produce something relatively perfectoid over the Farfontaine curve by taking the relative curve, right? And once again, you can restrict to a fixed untilt, getting something perfectoid over this fixed tilt. And this thing is all compatible. So this is the relative curve. So our construction somehow is a way to descend at a rigid level the construction of the relative curve that is well-defined and geometric at the perfectoid level. So it's a way to descend, stay in the rigid side. Okay? And this commutative diagram also shows that it is compatible with the tilting equivalence of perfectoid and of rigid motives. All right. And what is the final theorem that I want to state? It's actually so we have a well-defined functor from motives over K flat to OX modules. And this is not really interesting if we do not know anything about the properties of these modules, but once again, it sends something compact to a vector bundle. So this has the two good properties that I sketched at the beginning. It starts from equicharacteristic P, and it produces a vector bundle on the whole curve in a compatible way with the new de Rham cohomology on the tilted thing. And as you could see, hopefully, maybe not, it has also a geometric feeling because it is a way to descend the relative curve construction to the rigid level out of some homotopy business. I think I will stop here.
Is this working? Yes. Are there questions? I can ask a question. Could you say a little bit more about the de Rham realization that's still on the board there?
Yeah. You can always pretend that this has an overconvergent thing, so you can simply copy down this would be a relative version of the overconvergent de Rham complex.
So when you talk about de Rham complexes, right? You take differentials relative to something. What is the
base, which is KXF.
Okay.
So everything will be.
I see. So these are spaces over XF, and then
yes, XF is not equipped with it's not equipped with the overconvergent structure, but you simply choose an embedding of your thing into a strictly bigger one, and then.
Okay. Any further questions? If not, let's thank our speaker one more time.